Data rate limit is a topic of this session. Data rate is actually a very important consideration in data communication, and that is actually indicates how fast we can send data over a channel. That is how many bits can be sent in 1 second over a channel. And this data rate limit actually depends on three different factors. First one is the bandwidth of the channel, and second one is the level of the signal, how many levels we are using to represent the data, and the third one is the quality of the channel, how good the channel is, how much noise is present over the channel. So these three factors limits the data rate of a channel. And how to compute the data rate of a channel, we have some theoretical formula introduced by some scientists, and one is for noiseless channel, and that is found out by Nyquist, and the second one is for a noisy channel, what's the data rate, that is developed by Shannon. So we will see both of these equations. First one, for a noiseless channel, what is the maximum data rate that we can achieve, and such a formula was developed by Nyquist, and the corresponding equation is bit rate of a channel is equal to 2 into bandwidth into log L. And whereas this bandwidth is actually the bandwidth of the channel, and L is the number of signals levels used to represent the data. How many signal levels are there? That is actually L. So using these two factors, we can find out the maximum data rate of a channel. So bit rate is the bit per second over the channel. So according to that formula, the specialty here is that we may think that given a specific bandwidth, we can have any bit rate we want by increasing the number of levels, right? So actually number of logical level or number of signal levels is actually selected by the user, right? So if we increase the number of levels, bit rate also can be increased. That such a implicit indication is there in our channel, right? Yeah, that is directly proportional to this L. But theoretically that is correct, but the thing is that practically there is a limit. If we increase the number of levels, what happens? We impose a burden on the receiver, right? The receiver should be able to identify different levels, right? Then only it can correctly receive the data whatever sent by the sender. So if we increase the number of signal levels, the problem here is that the difference between two logical level will be decreased. That differentiation will be decreased if we increase the number of levels. So a slight noise also can make this interpretation of one signal level as another in the receiver. So the receiver, the corresponding circuit will be more complicated if we increase the number of levels. That's the problem here. So if the number of levels is just 2, the receiver can easily distinguish between 0 and 1. One level it is the data is 0, and the second level data will be 1. But if we, for example, if we increase the level of signal to 64, but the problem, the receiver must be very much sophisticated to distinguish between 64 different levels of signals, right? Yeah. In other words, we say that increasing the levels of a signal reduces the reliability of the system. There can be some misinterpretation at the receiver if there is a lot of signal levels. So by increasing the number of levels, we could never increase the data rate beyond a maximum, right? So we will see some examples for this data rate using this equation. So we have a sample scenario that consider a noiseless channel with a bandwidth. We are given the bandwidth of 3000 Hz, transmitting a signal with just 2 levels, only 2 levels are there. So what is the maximum bit rate here? Bit rate, we can apply the corresponding formula, 2 into bandwidth into log L, 2 into 3000 into log 2. Log 2 is actually 1, base of 2, right? So 6000 bit per second is the maximum data rate in this scenario. In second case, consider the same noiseless channel transmitting a signal with 4 signal levels. Here we have only 2 signal levels. We increase here the logical signal level into 4 different levels. Now we can see that 2 into 3000 into log 4. Log 4 is actually 2. That is 12,000. So by doubling the logical or signal level, the data rate is also doubled. So to a maximum extent, we can have this increase in data rate by increasing the number of levels. Beyond that, that will affect the reliability of the system. Another equation, we need to send 265 kilobit per second over a noiseless channel with a bandwidth of 20 kilohertz. How many signal levels do we need? So we are specifying here as we need to achieve this much bit rate, 265 kilobit per second bit rate should be achieved. So in that case, what should be the signal level? So we can apply this values into our formula. Bit per second or bit rate is given, that is 265,000, right? That is equal to our equation 2 into bandwidth into log L. Applying that values here, we will get log L as 6.625. That means L will be 2 to the power 6.625 is actually 98.7 levels. So usually the number of signal levels should be a power of 2. So rounding to upper or lower power of 2, either we can choose as 64 rounded to lower power of 2, right? Or it can be rounded to upper level, that is 128 levels will be there. So if we are choosing a 64 bit level, then in that case the corresponding bit per second, applying the formula again, we will get 240 kilobit per second. And if we are choosing 128 levels, the corresponding bit per second will be 280 kilobit per second. So this will be the answer. And coming to the second equation, that is to find the maximum data rate in the case of a noisy channel, we have another equation developed by Shannon. And obviously in a real-time environment, the channel always will be noisy, right? There won't be any noiseless channel. So we have to apply this formula in that case. And in 1944, Claude Shannon introduced a formula called Shannon capacity to determine the theoretical highest data rate for a noisy channel. And the corresponding equation is capacity of a channel is equal to bandwidth into log 1 plus signal to noise ratio. So since there is noise, signal to noise ratio will be one factor which affects the data rate of a channel. So this is the equation. So we can say that in the Shannon formula, there is no indication of the signal level. No matter how many levels we are using to represent the corresponding data, there is no contribution from the signal level to the data rate. So we cannot achieve a data rate higher than the capacity of the channel. Always the bit rate limited by or defined by the capacity of the channel. So we'll see an example. Consider an extremely noisy channel in which the value of the signal to noise ratio is almost 0. SNR is 0. That means all the data we are transferring will be converted into noise, completely noisy channel. In other words, the noise is so strong that the signal is faint. For this channel, if we apply the corresponding formula here, channel capacity C is equal to B, that is bandwidth into log 1 plus SNR, B log 1 plus SNR value is 0, B log 1 is log 1 is actually 0, right? So B into 0 means 0. So if the channel is completely noise, we cannot transfer any data over that channel. And second, we can see an example for a normal telephone line. We can calculate the theoretical highest bit rate of a regular telephone line. A telephone line normally has a bandwidth of 3000 hertz. That is, it starts over 300 hertz to and upper limit is 3300 hertz. So bandwidth is actually the difference between high and low frequency, right? That is 3000 hertz. And the signal to noise ratio for this normal telephone line is actually 3162. So by applying those values into our formulas, C is equal to channel capacity is equal to bandwidth, that is 3000 into log of 1 plus 3162. Applying then computing the value, this is 34 kilobit per second, 34.86 kilobit per second is the maximum capacity of bit rate we can achieve over a normal telephone line. So if you want to improve the corresponding bit rate of a normal telephone line, either we have to increase the bandwidth or we have to increase the signal to noise ratio. Another example, we have a channel with a 1 megahertz bandwidth. The signal to noise ratio for this channel is 63. What are the appropriate bit rate and signal level? So in case of bit rate, we can find out using this Shannon formula, right? And for signal level, we have to apply that over a noiseless channel, that is for applying the Nyquist equation. So coming to the first one, to find out the bit rate, use the Shannon formula. C is equal to this equation, applying that we have 1 megahertz, right? 10 raised to 6 log 1 plus and SNR is 63. Applying these whole values there, we will get 6 megabit per second as the maximum bit rate that we can achieve in this condition. So Shannon formulas give us 6 megabit per second. That is the upper limit. So better performance, we can either choose something lower. Some lower value will be more beneficial. So we are choosing 4 megabit per second, for example. Then we use the Nyquist formula. Okay. So this is the maximum, right? For better performance, what we are doing, we are not utilizing the maximum, but we are taking another value which is near to that. That is 4 megabit per second. Now we have to find the number of signal level we can use in this case to achieve this much bit rate. Okay, for that we can use the Nyquist formula. Nyquist formula, applying that into Nyquist formula, that is bit rate is equal to 2 into bandwidth into log L, right? Bit rate we are already chosen as 4 megabit per second, bandwidth is 1 megahertz, and applying those values we will get L as 4. So the Shannon capacity gives us the upper limit of a channel, and Nyquist formula tells us how many signal levels we need.